here's a scatter plot, and we know from past experience that our routine here is to choose a model that might best fit this information and then go through the regression equation and so on. Well, if we're just comparing or looking at this model in terms of what we're studying in this chapter, the exponential and logarithmic functions, we would choose a logarithmic model to emulate this data, because after all, the data points tend to be going up right here, and they tend to be flattening over here. So a logarithmic model would be more appropriate than the exponential model for this data. Now, I just want to compare these two. We'll kind of extend the conversation in just a minute, but I want to compare a couple of scatter plots. This is one, and there's another one that I have entered onto the calculator, but I need to get rid of this one. I'm pressing second and then y equals, and I want to turn this plot off. This is the plot that we've been looking at, but I'm going to turn this one off, and then I want to turn this one on because I have some information here. And I'm pressing graph. Now the window settings are the same for the two scatter plots, so I didn't have to deal with that. But notice that in this one we kind of start out flat and we kind of ramp up here on this end. And this is the kind of model that we might think would be exponential if we're just comparing exponential and logarithmic models. The other one would be logarithmic, this one would be exponential. But you know, when we see a model like this, or excuse me, when we see a scatter plot like this, there are a lot of possibilities for models. We could think that this is part of a parabola, for example. You see, so a quadratic model might fit this fairly well. An exponential model might fit this well. A cubic model might fit this well. Let's see which of those three fits this information best. And we can tell by doing this. I'm pressing stat, and now I want to calculate a regression model. And I'll cursor down to the quadratic regression first. It's just the first one that I hit here. And here it is. Now notice the r-squared value. I have diagnostics on my calculator, and this gives some information about how good the fit is. It's a pretty good fit. Now another way to tell about the fit would be to do this kind of thing. Let me press y equals and get this on board. These are some old equations. I'm just going to get rid of them. All right, I want to bring in the regression equation, and I'm pressing VARs and then cursoring down to statistics and then over to equation, pressing enter. Here it is. And now the graph. All right, it seems to fit the information fairly well. What we can do to evaluate this, I kind of recommend using the calculator, but if we press trace and we trace over to a particular value like, oh, this one, 4. Now this is a data point. This is 4, 1.8, and it's that data point, this data point where the icon is flashing. If we jump down to the graph, now we're not going to be on this point when I jump to the graph. We're going to be right in the middle of the graph. But if I cursor over and create friendly settings, I could land on an x of 4. Now, and I can't quite land on it here. I would need friendly settings in order to be able to do that. Let me go ahead and go to that trouble. Window settings. I have a 1.25. I have 10.25. I need a total horizontal distance of 9.4. Gee, I can accomplish that rather easily by adding 9.4 to 1.25. Actually, I could do this. I could just take this and make this 0, 0. That's 1. And add 9.4, and I get 10.4. So I'm going to input a 4, 0. And now let's look at the graph. See, it's pretty much the same view, but when I press trace, I can actually trace to that 4 business that I was talking about before. And here I go. I'm just going back to it. I'm on the graph of the curve now, and I'm going to go back to 4.0, just an x of 4. Now notice the y value, 1.5, 0, 2, 1, 6, and so on. Now let me jump to the other equation, or excuse me, to the data points, and I have 4 and a 1.8. You see, so what we do is we take the same x value on data points and also on the graph, and we compare the y values, and we want the difference between those two. So I would jump to the graph, and there it is, 1.5, and I'm comparing it to 1.8. You see, and you take the difference between those two y values, and you add all of the differences, and you recall how to do that, I'm sure. And we were squaring those differences, and the least squares is the one that fits the best. Well, I think a more prudent way to proceed is to just let the calculator do all of the work and look at, turn diagnostics on and look at the r-squared value when the regression equation comes up. All right, let's take a look back at that. The r-squared here is 0.99346. All right, we want to probably make a mental note of that. That's the quadratic regression equation. Now let's go through a different regression. We can press stat, right arrow, and let's calculate another one. How about a cubic regression? And going through that, remember the other one was 0.9934. Oh, this is a better fit, 0.9965. That's closer to 1, and therefore this is a better fit. Let's see how much better it is by putting it onto the calculator. I'm going to jump down here and press VARS, and I want item 5, and right arrow twice, and bam, there's the equation, and here's the graph. Now I'm overlaying the graphs with one another. They appear to be right on top of one another. I want you to notice, though, the digression of the graphs here and up here. And it's probably in those areas of difference where someone would make a determination of which of these two models best fits this data, particularly if you're trying to get information which is outside of the data set. If you're looking for information back in this direction or information in that direction, then you might make a judgment call as to which one of these models is going to best fit that data. Well, at any rate, we're not finished here. Let's go back to the main menu and recall that this is 0.9965 for the cubic regression. Let's go through another regression. Let's do the, well, gee, we're studying exponential functions here, so let's go through that. We want an exponential regression. Here we go, exponential regression. Now remember, that previous one, the cubic regression, had an r-squared of 0.9965. Let's see what this one does. I'm pressing enter. 0.997. This one is even better than the other one. All right, so let's enter this one onto the calculator. That is, let's press y equals and make the calculator pull this one on board. And VARS, statistics, right arrow, a couple of times, press enter, and that one's on board, and now it's graph. Still looks the same as the others, doesn't it? You see, it even kind of filled in the information right here. Well, let me show you how you might make a determination here. We know that the exponential regression was the best fit in terms of r-squared value. But if we're using this for some indeterminate reason at this point, then we might look at the graph outside of the data set. That is, we might go with, now let's see, I still would like to have, I might want to have friendly values, so I'll double the 9.4 and go 18.8. And actually, I'm going to go with something like a -5 right here. I want to see this graph on both sides. And an 18.8, the -5, that's 13.8. And let's see what this does for us. Now, what I really want you to see is how the three different graphs are so incredibly different on this side. You see, and they'll be different on the other side as well, maybe not as much, but let's take a look at the high side. I'm not as high as I'd like to be on the graph, I'm noticing here. So I'm going to change the window on the high side, the Y max, to maybe something like 20. And now let's see if we get a sort of a digression of the graphs on this other side. All right, the third one is being drawn at this point. Wow, that, that third one is right on top of this other one. But you notice that the graphs are beginning to have find their own path, and it's a path different from the other one over here. They digress a great deal on this side, not quite as much over here. One of the graphs is right on top of the other one still here. But we could go even further out and find digressions in the various graphs. And in that way, we can make a determination of the best fit. Here's a table showing the amount of revenue collected by the Internal Revenue Service for the years 1960 to 2000. Let's enter the information into the calculator and choose a model and generate a regression equation and actually make a prediction for the amount of revenue collected in the year 2008, a year outside of the data set. Well, we begin by entering the information. I'll press that and then enter for edit, and notice that I've already entered the information. The important feature here is that 0 corresponds with the year 1960. So 1960 is the basis year. And a number like 15 here means 15 years beyond 1960. Oh, that would be 1975. So the amount of revenue for 1975 is this value from the table. All right, so let's keep that in mind as we go through the problem. It just makes this business of establishing a basis year and so forth just allows us to make it a little bit easier to set up the window and a little bit easier to enter the information. All right, let's look at a scatter plot. Now, I have already turned the plot on, and to establish an appropriate window, I'll press zoom and then select item number 9, zoom stat, pressing enter. Here's our information. Now, the scatter plot seems to be rising over here, and we saw from the earlier problem that there are several models that might be appropriate for this situation. The exponential model on the earlier one was a better fit. And let's use an exponential model here because we are studying exponential functions in this chapter. So we'll go through the stat, and then we want to calculate, so I'm pressing right arrow, and I want the exponential model. Let's go down here, exponential regression, here we go, and pressing enter once again. Now diagnostics is on here, and I have my R squared and my R values here, and notice that they're pretty high values. They're pretty close to 1. We ought to get a very good fit here for the information. Let's press Y equals and get the calculator to input this equation for us. I'm pressing theirs and then down to item 5, statistics, right arrow twice, enter, and here's the equation on board. Now, by the way, I'm pressing second quit here to get back to this. The A value is 88.57. We could actually write this equation in algebraic form. You know, we could round this to the nearest hundredth. We could round the B value to the nearest hundredth maybe, or maybe the nearest thousandth. And we could actually build this equation algebraically. And the question that we're asking could be calculated algebraically. It'd be a fairly easy thing to do it that way. But in doing it that way, we are almost forced to round this long decimal. So we get a little more accuracy, I think, by using the calculator for the entire, to answer the question in its entirety. Well, let's see, we're at the point where we're ready to graph, and I'm overlaying the graph with the data points, and we see that the graph is a pretty close fit with these data points. Now, we want to find out something about the revenue collected in the year 2008. Now, remember that the values on the x-axis, these were years, and we started with a 0 and so forth, and there are years, the basis years, 1960 and so on. So these are years, and the vertical axis corresponds with amounts of revenue. Notice the amount of revenue is going up. Well, it's literally going up exponentially, you see, from year to year. Okay, to get to that point of 2008, we might press trace. We're on data points here, and I'll just cursor over a little bit to show that. And the down arrow key puts us on the graph. But cursoring on the graph gives us unfriendly values. We want friendly values when we trace in order for us to land exactly on the value corresponding with 2008. So I'll go to the window and try to set up something appropriate for this graph. Now notice, -4 to 44, wow, that's a horizontal distance of 48. You see, now I want something that would be a multiple of 9.4. It really doesn't, we can just make this very easy on ourselves. The appearance of the graph doesn't make so much difference at this point in the problem. In fact, I can make this the x minimum 0, for example, and then an x max of 94. You see, that's a 9.4 times 10 would give 94. Now, I know that since this is exponential, the graph is rising to the right, so I might change my y maximum from 2437 to, oh, let's say 5,000. Now, I just want it to go way up, that's all. Now, here's the graph. See, there's my little scatter plot, and the graph is just going way up like that. All right, now, when I press trace, I'm on data points to begin with, and I'm pressing the down arrow button, and the calculator is still calculating. And when I press the down arrow button, I'm on the graph, and I'm way up here near the top. But this is 47. Now, wait a second, what do I need for this? Well, I need, let's see, the year 2008 would be 48 years from the year 1960. You see, 1960 was the basis year. And 1960 to 2000 is 40 years. 2008 would be 48 years from 1960. So I want an x of 48. And I'm just pressing the right arrow button, and bam, I'm right there on it right here. So I would predict then that the expectation would be that the IRS would collect this many billions of dollars in the year 2008. To estimate the amount of defoliation caused by the gypsy moth during a given year, a forester counts the number of egg masses on a fraction of an acre. Now, the fraction is 1/40th of an acre, but it's a circle of radius 18.6 feet. It's a pretty big area, you see, and so the forester is counting the number of egg masses within that region. And the count is made in the fall. Now, the percent of defoliation the next spring is shown in the table. So we have, with no egg masses, there is still 12% defoliation. With 25 egg masses, 44% defoliation, and so on. So that's what this all means. The purpose of this is for us to take a look at the scatter plot and choose a model. And it's a rather interesting pattern. Now, I'm pressing Stat and then Edit, and once again, I've already entered the information into the calculator. Notice that there are very few data points here. And the scatter plot, see, the plot is already on. I'm pressing Zoom and then Zoom Stat to get an appropriate window. Now, what we're noticing is, and by the way, the first data point is right here. So this curve is kind of going up like this. You see, it's angling up almost exponentially right here, and then it's leveling at the top, and that is the classic form of a logistic model. And we're going to use a logistic model here to see if we get a fairly good fit. The logistic model in the calculator requires a lot of power. If you have a lot of data points to deal with, then the logistic model may not be a good one to choose on some calculators, because it just takes a long time for the calculator to make the calculation. This one isn't too bad, though, with let's see, 5 data points. So let's see, we'll press Stat and then right arrow and then down to the logistic model. There we go. Pressing Enter and Enter again. I notice that just with 5 data points, it takes a little while for the calculator to make the calculation. Just imagine what it would be if there were 10, 15, 20 data points. Well, let's see. Here's the form of the algebraic model, and here are the values of the A, B, and C within the model. Now, notice that there is no, even though I have diagnostics on, there is no R squared value here, but we can see the goodness of fit by putting this onto the, overlaying it onto the graph of the scatter plot. I'm pressing Y equals and then vars down to 5 over 2, enter, there it is, graph. wow, this logistic model is very, very close. It seems to be going through every single data point, as a matter of fact. So this is an extremely good fit. And that's really what we wanted to see in this problem. How to generate, or how to look at a scatter plot, determine that the logistic model might be appropriate, and go through the process of generating it and overlaying it with the scatter plot.